this introduction, I want to also introduce our first speaker of today, who is Dr. Stanislav Dashevskyi from Forescout, and he's a security researcher there, with his research focusing on open source software, software security, and vulnerability analysis. And today, he's going to talk about routing network gateways.
Thank you. Hello and welcome. Thanks for being here. I really appreciate it. And yeah, its title sounds complex, but it's basically some experience I have accumulated over the years that will help you to get started with vulnerability research against various networking appliances. A little bit about me. I did my master's in automation and control systems, so it's very far from cybersecurity. I would say it's completely the opposite of that. And then, by some coincidence, I got into cybersecurity, namely the field of software security, and I cannot seem to find my way out. I've been working together with Francesco Laspino, who could not be here, on the content that you will see in the next slides. So it's our joint work, basically. And the things that we do vulnerability research against networking devices as our daily jobs. Right. So the bootstrapping probably was the wrong word. What I will use here is a term called routing, is essentially getting a root access on a network device for various purposes. And for us, as vulnerability researchers, this means that we can finally start our work. But maybe for some of the attackers, that's the actual end goal. So I will talk a little bit about this, and I will show you some of the interesting examples from the last couple of years. And of course, there will be some new vulnerabilities that I'm going to show to you today. Finally, I will tell you how we did that, and with a little of the demo at the end. Right, so why do people decide all of a sudden, let's root a router? And here I'm using the word router, but what I really mean is any box that sits on the network and can basically do or manage different kinds of network communications. For example, yesterday there was a presentation that mentioned edge devices, and those are different devices that sit on the edge of the network, and basically they give VPN access in and out of your organization. And if those are compromised, you are in trouble. And by nature, they are exposed online, so you cannot avoid that. The situation is that most of these devices, doesn't matter if it's a rugged enterprise VPN concentrator or a router you have at home, they are sort of closed down. Most of them run Linux, which is open source. They use a lot of open source components, but not all of them, if any of them, allow users to actually gain root access and to modify any of the software components inside. And the reason why I do this regularly is to facilitate vulnerability research, because static reverse engineering is cool, but in a complex operating system with complex binaries with thousands of lines of code, reversing statically, I can think of an analogy by, let's say you have to demolish a brick house, but you have only a teaspoon. You can admire the skill, but it's a little bit unpractical. So always do a dynamic reverse engineering if you need to understand complex protocols or how the binaries really work as a whole. So the reason for routing for me is so that I can install debugger and get a sort of inside perspective of how things work. Often the firmware is encrypted, so it's a sort of a chicken and egg problem. So if somehow you can root, you can get the decryptor binary so you can decrypt the rest of them, or you can just dump the file system and continue with your work. Of course, it's also for exploit development. If you have debuggers, the job is much easier. And like I said on one of the previous slides, for most people, that's the end goal. For me, it's just the beginning. Because what we do at Forescout, we actually provide exploit detection, mitigation, and also basically the visibility over the network. So we have to know how these proprietary networking protocols work. And for some people, it can be for fun. For example, you have an old router that is still good, but it's end of support. So you want to install open source software in it, but the vendor forbids it. So how do you do it? The same way. And of course, there are bounty programs. I heard they pay handsomely for remote code execution bugs. and of course, doing crimes. That's always on the table. I mentioned they run these boxes that you see on your networks or don't see. Hopefully you see them. They run different kinds of Linux, and you may think there are many different vendors that have many different operating systems, but essentially it's the same. So this basically is a snapshot of genealogy of an open source router operating system called OpenWRT. And what you see here are probably dot, so I will explain. What originally was an open source project is now being actively forked and somewhat reshaped by many proprietary vendors like TP-Link, Zixel, Teltonika, D-Link. So what they do, they take a snapshot of that operating system, they do some modifications on top, they close source it, and they sell it as their own. And in some cases, they even have a fork of a fork. So that Teltonika RootOS, which was derived from OpenWRT, gave birth to the operating systems used by Unitronics and MDEX. So essentially, you see this proliferation of one open source project into all these proprietary systems. Why is it important? Because it actually creates problems. Recently, or not so recently, a generation of Wi-Fi 6 routers had to switch to the Broadcom system on a chip in order to support the new features. Unfortunately, OpenWRT doesn't support the proprietary drivers for that chip because they never had an agreement in place to do that. So the only way is to basically ship a closed source firmware blob as a driver within this open source operating system. And for OpenWRT, they simply decided not to do it. So there's no support for that. So vendors have to find a workaround by creating their own forks. And there was also a very nice presentation 10 years ago by Simon Wunderlich about the new FCC, and that is the Federal Communication Commission of the US. So they basically initiated a regulation which required the firmware vendors to lock down their firmware to prevent users to tinker with some non-compliant parameters like the Wi-Fi frequency and whatnot. And they, especially forbade these vendors to make it possible to install a custom firmware such as OpenWRT. So for that reason, it was locked down in the US, and because US is a large market and its economy of scale, I think it was basically affecting the rest of the world too. I'm not saying these are the actual reasons why the vendors are doing this, but I'm suggesting that as a possible explanation. Right, and this firmware lockdown is not actually a good idea from many reasons, because many of the devices that you see on the market now, they're actually designed around OpenWRT, so it will not likely go away even in the next years, but what you have different kinds of snapshots that they create and freeze with custom coding on top, and those snapshots have various degrees of freshness because it's very hard to patch a firmware blob. It's very easy to patch a certain component when you have an open system, but for a firmware blob, you have to adhere to the release cycle, you have to test things properly, so it's a very long process. So vulnerabilities, especially in third-party software, they tend to accumulate. And of course, because of the stuff that I already mentioned, these proprietary derivatives of open system are unlikely to provide root. So we now end up in a situation when you buy a box, but you cannot modify anything inside, despite the fact that you own it. So there is another consequence that I want to draw your attention to, is that this kind of situation also leads to the fact that the users have hard time to inspecting the firmware or the software inside, and it makes it also harder for the vulnerability researcher to get inside and to see how things are. So vendors might try to get away with long release cycles and some things that are overdue patching. So if you want to actually look what's inside of your router or somebody else's router, hypothetically speaking, you have to begin somewhere. And there are several ways. I'm not considering here hardware hacking or covert channels or anything like that, because actually things are way more simple than that in most cases. So what you can do actually, you can read the documentation or use guides or forums, because there is a good chance that somebody has already done that, but they never published it for a wider audience. So that's the first thing to do. Then, because I mentioned these are complex systems with lots of open source components, there might be some historical vulnerabilities that you may want to consider that are still unpatched. And those you can use to actually try to root the device. And of course, there are such things as recurring vulnerabilities, which means that the vendor, or let's say the maintainer of certain projects, make the same mistakes. So you can basically try to see if maybe they forgot to fix something that you can easily find. Of course, the hardest thing is finding a new vulnerability and popping the root shell, which everybody seems to do, but it's the hardest of them all, except the hardware hacking that I already mentioned. And in terms of the functionality or points of interest in the implementation, you want to see if there's any technical support feature that looks like backdoor. If it's walk like a duck, it's probably a duck, but we'll go with technical support feature, and I will show some examples later. There are also things like software composition, which I mean the vulnerable third-party components that you can always rely on. And of course, things that are most likely exposed online is the administrator panels, web UIs, and whatnot. And specific attention should be paid to things that basically translate setting from the user LAN into the device itself. So basically the pipelines between the admin panel and the configuration files on the device. So here is the first example of the device we did a couple of years ago. It's a Sierra Wireless LX60, I believe. You can see it on the picture. It's a rack device that takes a SIM card in, and it's used as a network gateway in places where you don't have any traditional network connectivity. One of the use cases is some of the police vehicles, also field hospitals and things like that. So it's not a device you can find at your home, but from the inside it looks very much the same. And what they had actually on their website, and here I have to mention, it doesn't allow you to SSH into it or have any admin access despite the web admin panel. On the website, they have a guide that says, if you have troubles with your device, you can enable what they call a diagnostic shell. And then you call the technical support, you give them basically access, and they can fix the problem for you. What it actually means is that when you click that button, enabling diagnostic shell, it will write the hard-coded root password into etc password file, so that there's basically a hash of it. And if you have enough computational power, you can crack it and then basically gain access to any of those devices, because that's not the only one device that has this feature, but they practically use it elsewhere. We did not do it this way because it was a fairly complex password, and we were just beginning, so we were wondering if we could do something else in this case. And here I'm coming to the topic of the vulnerable third-party components. That's a big thing because I want to give you an example of the study we did a few years ago when we looked at the TCP/IP stack implementations for embedded devices. And this is essentially a component that implements the whole thing from the Ethernet communication up to the application layer. And turns out there's about 13 or 15 open source implementation, and as many of them also are implemented by companies and are closed source, but probably there are many more. And the thing is that we analyzed about 20 of them, and we found 100 vulnerabilities, and many of them were critical. And they were there for many, many, many years. So if you look at the trickle down of this bug, let's just think about it. Let's take one vendor, let's say Siemens. They had NOT-EX, I think it was called, the TCP/IP stack. So what they did, they implemented the TCP/IP stack. They put it to a certain operating system running certain PLCs or medical devices. And then they decided, okay, it's a good, successful product. Let's sell it to other companies so we can white license it and they can also use it in their products. And what you can see, basically, it then goes exponential. It can be a network management card or any other component used in other hardware or a different device itself. So basically, one single bug can affect not only multiple devices, but multiple vendors. So this is why, for the impact, we also look for these kind of issues. And this is why third-party components are the first thing that we looked at when we search for exploitable issues. This is an example from another study we did specifically on 5 router operating system, 4 of which were direct derivatives of OpenWRT. And this was the several snapshots we took. So this was the latest version of each of them. And we used certain tools to try to understand how outdated the open source components are, what are the potential historical vulnerabilities, and what is the risk involved in that. And as you can see, in all of them, except maybe Tonica, it was quite a lot. But all we know, it takes just one vulnerability to pawn a device. So this all represents risk and basically reinforces the point I made about the closed clones of the OpenWRT. Back to Sierra Wireless. So here we took the approach of looking at third-party components. However, the finding that I had at this point was a bit unexpected. Normally, you would find some known vulnerability or some component that is known to be bad, and you try to exploit it. However, if you see a component that is quite mature, is used in a lot of places, but doesn't have any vulnerabilities on the NVD or any other sources, this is where you have to pay even more attention. We had found that Sierra Wireless is using OpenNDS, which is an open source component used for setting up captive portals. So basically, in this hotel, you have one. You connect to the free network, gives you a pop-up, you insert a fake email address, you insert a fake one, and then basically lets you through to the internet. This is exactly what it is. And also, it's interesting to note that this component is a standard package of OpenWRT. So basically, they just carry it over. Unfortunately, the version was a little bit older than the upstream, but whatever we found there, it was 14 bugs. They were all affecting all the versions from the version 1 until the version 10, I believe. And in this particular case, it was a very interesting vulnerability in which you just interact with the captive portal itself. So it acts as a web server, and basically you can set the web request, and part of the web request is a query string. I will not explain what it is, I hope, because you are at the technical session, you know, but if you have questions later, I will be happy to do it. So basically, on the top, you can see an example of that request, just querying the root page, sending a query string, and it works. The problem here is that it's defined to be finite, and it's allocated on this stack here. And basically, if you send a query string longer than this amount of characters, it's a classical Stack Overflow. The trouble here is that they didn't even parse it correctly. So in order to exploit this vulnerability, we have to work around other bugs within the code, which was a little bit interesting. But yeah, again, if you're interested in that, you can ask me later. But what it essentially means is that it was a very simple bug with very bad consequences for the whole system. So essentially, I will spare you the details. To bypass some binary protection, we had to use very simple return-oriented programming chain. And essentially, we turned this benign request into this simple command with some shell code in between that basically gave us a root shell. And because this project actually requires tools like ifconfig or other things to manage and segment the virtual network, it runs as root. So it doesn't require any elevation of privileges. And this is how we rooted it, basically. And this gave us insight into the inner working of the device so we could do more research. The second example is drastically different from the first one. So this device is this big. It looks actually like a server rack rather than a networking device, and it's very powerful in terms of computation. And this is another example of what I was saying earlier. This is more about recurring vulnerability. So before we even started, we looked at vulnerability reports, and we found a very interesting pattern. They had quite a lot of OS command injection and stack buffer overflow vulnerabilities. So the first one are marked in red here, the other ones are in green, so you can distinguish. And it was practically the same functionality, the same bugs all over again. So we thought, okay, from our experience, vendors rarely do any kind of variant or root cause analysis, so whatever you report to them, they all just fix that and move on. So we thought maybe there is a chance that they have missed something and we can find something similar to this. And before I actually explain what we did, I just want to give a little bit more of a context, because usually when you think about networking devices and some kind of embedded Linux, you have basically stuff that runs on bare metal, you have some Linux binaries, some Linux protocol stacks, and you have the custom binaries they add on top. And this all works as an ecosystem. In this particular one, and that was the first, this actually has the entire operating system virtualized. So it runs in a QEMU inside of the Ubuntu box. And the Ubuntu box is basically the real operating system. And there are some other binaries that basically manage that operating system, but it's completely closed, it's virtualized. And the thing with these stack buffer overflows, most of them were not exploitable, so usually it leads to a denial of service, but with this kind of design, even if it crashes, it resumes in about 2 seconds. You don't even notice it, so it seems to be very resilient and effective design. What we found, if we found another stack buffer overflow within this virtualized operating system, which was pretty exploitable, but it didn't give you any root, because to get the root, you have to escape this sandbox, which usually requires some kernel level exploits and black magic. And then we decided to look how this virtualization was designed. So usually, this operating system that is virtualized, it has to talk somehow to the main operating system. And it happens to do that through the virtual serial interface. So basically, it sends some commands to the host saying, oh, I need a reboot, or I need my time updated, or I need other things. Of course, that's dangerous if you can send any arbitrary commands. But for that reason, they basically had a whitelist of commands, so there were only 10 of them that you can run. For example, this set Linux time is a member of that whitelist, and that's the only thing you can do. If you look at how it actually is executed, you may get some hints about what I'm about to show you next. And when we looked at the binary that actually implements the whitelist and the running, you will immediately see that here, this is all the unfiltered input, and this is where it ends up. So can you guess what is the problem here? Yes, but this one in particular, because what you can do here is that you can use that first vulnerability, stack buffer overflow, to contact this binary saying, oh, I need my Linux time updated. And then at the end, you can say whatever else you want executed after that as a bonus. And basically, this simple stack overflow here and this little bit of design decision allowed to basically escape that sandbox and get root on that Ubuntu operating system. So no kernel exploits were burned in the process. Finally, I would like to introduce our today target, because this was all the old stuff, interesting examples, but you want to see something new. And this time is a vendor called TP-Link. I don't know if you heard about the previous one, but this one probably is even more obscure, right? So this particular one is a device from the family called Omada, and it's based on MediaTek SoC with some Ethernet ports. It doesn't have any Wi-Fi, but it has a different use case. And in the past, in the recent past, it used to support OpenWRT in a way that, of course, it was designed for it. And on the OpenWRT wiki page, you could find a guideline of routing the device if you want to install OpenWRT on it. It led you to a GitHub repository that explained basically all you have to do is you have to SSH into it. You have a CLI where there's an undocumented command called debug. You type it in. It will ask you for a password, which is derived from the MAC address of the device and your username. And basically, you insert that, and then you get root as in the normal operating system. And then you can flash whatever you want. Last year, I saw there were some troubles in the discussion of that GitHub repository, and people were saying, oh, this tool doesn't work anymore. I cannot access the root anymore. What happened? And people were saying, yeah, probably they have changed something. I cannot even roll down the update. I cannot update the old version, so this doesn't work. What should we do? And turns out is that just a few months before, Cisco Talos found this backdoor, and they decided this is a serious vulnerability. They reported it to the TP-Link, got a shiny new CVE, and it was essentially fixed. And basically, you don't have any ability to root your device anymore. So we decided to have a look how it was actually fixed, and it was pretty interesting because now, so that you see the prompt at the top of the slide, now it requires you to basically sign a random string that they send you with a certain private key that you don't have. And then basically, if you should have it, then it will let you in. So they added some fancy crypto to it. But if you look at the actual implementation, I spare the details, but I put the right condition in here. If you have a certain file called image type debug present on the file system, the old way still works. So you can still log in using that password derived from just the MAC address and the username. Now, why they did that, I don't know, probably because they needed this for some kind of testing, but the problem was we could not use this path anymore for rooting the device because we didn't have the private key, and this file system doesn't exist, this file doesn't exist on the stock file system. So that was a problem. Upon looking at the code closely, I realized that the public key that they use to verify your signature is actually hard-coded. And it's the same public key used to now sign the firmware. So if it's a hypothetical situation, if a certain government has this key, it means they have access to all of your devices that basically run this firmware or some of the components derived of this firmware. No conjectures, just an observation. So it was still quite interesting to see if we can use some of this existing functionality to get in. And we could try to downgrade the firmware. The problem was we had to buy an old device. We had to do some tricks. And our goal was to analyze the new firmware anyway. So what I thought about that we need some kind of command execution just to help to create us these files so we can just use the old technical support feature to enter. And basically, for that reason, we had to find another target, look around the firmware, and see what will stick. And this is the actual target that we found. It's called Lucy. It's an integral part of OpenWRT. It's a very popular project used to configure embedded devices. It's basically a web interface with some scripts that translates changes you make through the web interface to the device configuration files. It's implemented using the Lua language, and yeah, it's really cool because it splits the interface logical parts into models and views, and basically allows you to do a lot of things without writing a lot of code. Specifically, why we chose it is because, again, if you look at the TP-Link's implementation of Lucy, you would see that in 2023, there was an issue with it that allowed to a lot of botnet creators, specifically Mirai, to hijack many of these devices. And this is an example of a proof of concept which is just a post request that you have to send, adding some shell command in one of the form parameters, and you're good to go. And because it runs as a root, it's very easy. Later the same year, Cisco Talos has found, I believe it's 8 vulnerabilities of the same kind in the same component. Looks very similar. So we decided, hey, we see something familiar here, let's try it as well. What you have to know about Lucy is that Lua scripts can be shipped as scripts, so you can read them. It's human readable code. However, you can also compile them into bytecode, and this is for a performance reason. They say also for a compatibility reason, and so that users cannot modify important settings. Anyway, so this is how it's shipped in Lucy. And normally you can, there are plenty of tools that, because there's a lot of metadata, rich headers and stuff, you can revert it pretty easily to the human readable code with the off-the-shelf tools. When we tried to do that with the TP-Link implementation, we got lots of errors and essentially nowhere, because it was telling us it's invalid bytecode, there's some junk in the header, so yeah, go figure. And at the same time, it runs very fine on the router itself, so we thought that there is some black magic with the Lua itself, or maybe they have modified the virtual machine or the parser or something like that. We didn't spend a lot of time seeing how they did it, but we at least could identify what they did. And for that, very quick and short introduction to Lua bytecode. If you want to know more, at the bottom of the screen is a very nice paper. So I encourage you to read it if you're interested. But essentially, there's a main header with the usual magic that you see in the binary files. Then there is a version which happens to be the same that TP-Link uses, and based on that version, you have different formats of the header. You have things like NDNS and then various sizes of different types you can find in the Lua file itself, including the number and the way this number should be interpreted. It's called the integral flag. So if it's 0, it's a floating point. If it's 1, it's an integer. And here I will show some examples. There are also things like function chunks. So each function defined in a file has its own header with its name, other things, and at the end of that header, you can see a constant list. So every constant defined in a function will be found here in a certain format. For example, this is a string constant where it starts with the number 4 always, and then you have the next number of bytes tells you what is the size of this string. And this actual number of bytes is dictated there in the header, so it's the size of an integer type. And after that, you have the actual value of constant terminated by 0. This is the easy one. The hard one is the number constant, because there are 2 bytes in the header that tells you how exactly it should be stored and interpreted. The 11th byte, in this case, it's 8, tells me that in this file, the numeric constants have 8, the size of 8. And the last, the 12th byte here is the, basically tells me if it should be interpreted as a floating point or an integer. And here on the left side, you can see an example of the same number encoded in a different way according to that header. And basically, you see, there are multiple ways of interpret things, and very easy to confuse the parser this way. So when we looked at how they actually have their bytecode and compared to the stock Lua, we immediately found that there are some irregularities. For example, they say, so on the left there is a header, they say that the integer is 8, while we couldn't find any integer of this size. And there is this very weird value for the integral flag. It's not mentioned in any specification. Moreover, things that looked like integer constants were designated by this number 9, which again is not present anywhere. So we decided, okay, let's try to fix it. And we did, according to specification, and it worked. So I don't know why they did that, maybe to prevent reverse engineering, but as you can see, it doesn't quite do it. And finally, we could interpret the numbers correctly. So then going back to the vulnerabilities I was talking about, we looked at what Cisco Talos did and how they patched this thing. And as with one of the previous examples, no root cause analysis was done, so we found one vulnerability that they have missed. And this one is concerning the field of the WireGuard VPN setting when you have to specify the private key. This is how it looks like. So the user input here is on the line 211, and it's passing through the function called save special string, which don't believe what it tells you. So as you can see, it's simply concatenated with the OS command, and then it gets executed in some way. So the problem here is that the function itself wraps the input into the double quotes, but the input is already wrapped into the double quotes. So that's the first problem. And in this way, you could escape this thing and create another command. Moreover, they did not escape the new line character. So basically, you can see here how the normal input will look like, and it will be accepted by bash. It will work as intended. But if I just change it slightly like this, adding a new line and a certain point, that call at line 216, IOP open, and interprets every new line as a separate command. So it basically takes an array of commands. And it will just execute whatever I put in after the new line. So basically, all I had to do is just to run this command to create that file or get a reverse shell or whatever, and it worked. So here are a few things about TP-Link's response. Surprisingly, they assigned CVEs to these things, and actually, I see that one is pretty high. The thing is that this was just something we were beginning with, and we reported other things to them, which unfortunately I cannot talk about because they will be only fixed in April 2026, I believe. That's the earliest date. But yeah. And the thing is, like I said, software gets reused a lot. So this is an excerpt from their advisory. So all of these devices are affected by these two CVEs. Essentially, if you have one of these and then you don't like the custom firmware, now you know what to do. I think the list should be longer, but I don't quite remember how many devices we estimated to be affected by this, but it's a lot. Yeah, and finally, just a little bit of demo. I will explain what happens here. So here I'm connected to the device. I'm SSHing into it. And here I'm showing you help. So as you can see, it's a limited shell with some things. So now I'm trying to put that debug command, and it tells me, no, you have to prove me with the signature that it is. Now I'm using one of the proprietary protocols that we reverse engineered after this to actually turn that OS command execution that was authenticated, I forgot to mention the one, into an authenticated one. And basically what I'm doing here, I'm simply creating that image type debug file, just asking nicely, please let me have the root. And it generates the password for me based on the username and the MAC address. And now I can try to do the same. And it would work because it's a video, but just to demonstrate. So now you see the prompt is different. And I find it very ironic that this banner is still present here. But yeah. So it's the end of my presentation. Thank you for bearing so far. Just a few things I wanted to mention before I conclude. There's always a way to root down the lockdown system. So vendor makes it difficult for users, for vulnerability researchers, but eventually one finds a way, and one doesn't need to have any hardware hacking skills to have solder at their disposal. We could have soldered a UART interface to this thing, but I just don't like to do that. So it's much easier to do it with just plain software vulnerabilities. Of course, study what other people did. So if that's your daily job, you can actually save yourself a lot of time. And finally, locking down OpenWRT, I think it's a bad idea and will only introduce more security issues because you also have a lot of custom coding on top that is not tested the same way. That's it. Thank you very much.
All right, thank you. I will open up the questions if there are any questions here from the audience. There's a gentleman right in the front. The microphone is already running towards you. Wait, it's incoming.
Hi. Thanks for your speech and making our routers less vulnerable. I assume you have heard about local network vendor MikroTik. Did you have a chance to play with it? And if no, why?
Very simple answer. It's on the list.
Thanks.
All right, from my side, the question is, in one of the examples you showed that you would craft an HTTP header and a request which requires a particular offset as well, so you need to know when to override the return pointer. I mean, you mentioned that Go dynamic, you do dynamic analysis. How would you identify this buffer size to override? Do you do static analysis of the frames? How do you approach this?
Yeah, one thing that I didn't mention, but there was a presentation yesterday about reverse engineering. You first emulate things as much as you can, but in the end you want to run it on the real device because this address will be different. There are other things in play that you cannot emulate if it's a more complex system, but essentially first, what I had to do, I had to use the emulator to test the proof of concept, and then when I had to do it with the real device, I had to actually find an information leak that will tell me the address of the heap. And because it's an ARM32 system and it had ASLR enabled, on these systems, ASLR is very inefficient in the sense that you can only have 2 base addresses for heap. One is more often than the other. So basically, once you know the base address, in 66% of cases, it's going to be the same. So it's basically one of the 2 possibilities. You calculate the offset to that buffer with that base address, and that's it. But you need to have information leak or some way to peek into the memory.
Right, for countering ASLR, you need the info leak or on the other way. Any more questions? All right, I will try to merge my question with one of the questions that's been provided to us over Menti. During your analysis of firmware, especially the routers that are from China manufactured, do you encounter some backdoors and some nasty stuff that's there and like undocumented functionality, or you just, oh wow, this shouldn't be there, besides any other vulnerabilities, right?
This was the example of those things.
Okay. All right, with this, I thank you so much for your talk. Let's give a round of applause.
Thank you so much. Thank you. It was very, very good. Thank you.